Hello forensic scientists and welcome to Forensic Glass Analysis. In this video we will address 5 different questions and then at the end we'll do a live demonstration on breaking glass using a projectile and then looking at the fractures. So the first question that we'll address is glass a solid or a liquid? What state is glass in? What is it made out of? What's the composition? The third thing is we'll ask the question, what are the different types of glass that exist? And also we will look at 2 different ways a sample can be matched to the crime scene and discussing the different physical properties of glass. The 5th thing is, from looking at fracture patterns, can we determine from which direction a bullet or a projectile came from? And then lastly, we will go through a demonstration. We'll take a piece of glass, a glass pane, and shoot a projectile through it, several, and then look at the stress marks, look at the fractures, and see if we can determine from those marks which direction the projectile came from, and from there that will allow us to help rebuild the crime scene. All right, let's get started. So there has been some misconception in the past because people will go to outdoor museums or those storefronts and they'll notice that with these old windows that the bottom of these window panes are thicker at the bottom than at the top. And so the conception is that the glass must be pulled by gravity over a period of time. And while gravity does have an effect on glass, it would take millions of years to even notice that effect. So why then is glass thicker at the bottom than it is at the top? Well, it's how it was made back in the day. In the old days, the method was called the crown glass method, which is you use a blowpipe, you take a molten pile of heated up glass, and you blow into it, and you take a spindle and you basically spin it into this monster globe like 5 or 6 feet tall, a huge bubble essentially. And then you cool it down, and then you begin to cut it into squares. And as you move towards that spindle, the glass gets thicker and thicker. So for each pane, you'll actually have a thin end and a thick end. Well, when you go to install, builders figure, it's more stable to have the thicker end down and the thinner end towards the top. So that's why the thicker ends are always towards the bottom, not because gravity has been pulling down, moving it, but because that's just the orientation that builders will put it to make it more stable. That's all. So we don't categorize it as a liquid, but it's also not a crystal. If you look at this top structure here, this is a crystalline structure like sodium chloride, where the atoms align themselves perfectly and you have this perfectly homogeneous. But in glass, the atoms don't align perfectly, and therefore we categorize it as an amorphous solid, meaning a solid but without a clear shape. Now we go into, what is your typical glass made out of? There's 3 main components, and it can be composed of even more things, but for the most part, typical glass is composed of roughly 75% sand, or silicon dioxide, or you could just say silica, sand. And then you also have lime, and why would you put this lime in? It's also calcium oxide. So what does the lime do? It keeps the sand from dissolving in water. It basically keeps it insoluble. And then sodium oxide is added in order to lower the melting point. Why? Well, because glass has to be heated to a very high degree in order to mend them together, to melt them all together, and then put out in sheets and then cool down. Well, sodium oxide lowers the melting point so that way it doesn't have to be heated to such a high degree. And of course, there can be other ingredients added to make different kinds of glass, but these are generally the three main ingredients that you'll find in most of the glass out there. So there's tempered glass. Tempered glass is soda lime glass, your typical glass, and it's used in the sides of car windows and in the rear of cars, and it's stronger than normal glass due to the rapid heating and cooling in the process of the glass surfaces. It's relatively safe in the case of accidents because when it breaks into very small, relatively small fragments rather than your big shard pieces like what would happen when you throw a baseball through a house window, for example. Instead, the pieces break into very, very, very small pieces, and therefore it's less likely to, impale a person upon impact. Cookware also, like Pyrex, is also tempered glass. We also have laminated glass, and it's basically, and so this is used in the front window of cars, the front windshield, and it's basically a sheet of plastic sandwiched between two sheets of glass, and so the glass is pressed into the plastic, and therefore when it breaks, it doesn't even really break. When it cracks, when there's an impact, it all pretty much stays the same. It's just like you've seen in movies. And of course, this makes it even safer than your tempered glass. You have your glass bottles in your house windows, and these are also soda lime glass. It's considered made out of the same composition, but the heating process is used here is the easiest of all of them that have been discussed so far, and the fastest. Thus, when they break, the pieces break into relatively large shards, which is why you can push on a house window and you feel like it's going to break, and when it does, it's like very, very large pieces. Well, it's the easiest and cheapest way to process to make the glass, and therefore it's used in that kind of construction because, well, how often does a house window break versus the risk in cars, in automobiles. And then you have crystal glass, like what you find in champagne glass, wine glassware, glass that you crystal, right? Crystal, glassware. The fine glassware that you find at fancy restaurants and that kind of thing. It's not the typical soda lime ratios, but it can contain up to 30 or 40% barium oxide or zinc oxide. So rather than your sand or your silicon dioxide, it'll be composed of barium oxide or zinc oxide, along with the other ingredients, and so it has. So why is it so elegant or so beautiful? Well, it has a high refractive index. It's glittery. It's sparkly to the eye. That's why it's so beautiful. Because of that high refractive index. And you got your phones, you got your iPads, your tablets, all those mobile devices. Those screens are made out of aluminosilicate glass. These screens are, once again, mostly silicon dioxide, like in glass bottles and just like we've been talking, but they also contain aluminum. So with the right heating and melting and cooling process, these screens become strong and thin and durable and resilient to scratches. And so along with aluminum, it's also, a very special formation process, heating and cooling, to make that clear glass, clear, strong, durable glass that we all know. All right, now we are into looking at analyzing the fractures, the cracks of glass. The penetration of window glass by a projectile, whether it's a bullet or a stone, produces cracks which radiate outward. So if they radiate outward, they're called radial fractures. And if they go around in a circle, they're called concentric. By analyzing the radial and concentric fracture patterns in glass, the forensic scientist can determine the direction of impact. So say you have a projectile and it's moving to the right of the screen. Here's your piece of glass right here, and it's moving to the right. It's moving towards the right. It's going from left to right, so it's going to impact right here. The radial cracks are formed first, and the reverse side of a radial crack are the back side is always larger. It's like it blows out the back. Whereas the concentric cracks occur afterward, starting on the same side as the force. That's why when you're looking at this this depiction here, you see how this side is actually it's almost like this side has been blown out. This side, the front side, the side that the projectile came from, cracks before the other side. With radial fractures, it's the other way around. So just pay attention to this. This will come in handy at the end of the video also. So this is a radial fracture. This is from this, looking down the edge of the glass, you can tell radial from concentric by looking at how much is missing. If the front side is missing, the side that you have the projectile coming from, it's a concentric fracture. If the back side is missing, it's a radial fracture. This is one way you can determine if it's radial or concentric. Now, let me just skip this slide for a second. Now, if you're looking at it from the front, well, this is a radial fracture. This is a radial fracture. Radius moving outward. But the concentric, this is a concentric fracture. Okay. Now, another thing that you can use to determine radial from concentric is by looking at the stress marks under a dissecting scope. The mnemonic device is RRR. Radial fractures form right angles. You see this angle right here? This is fairly right angle. Look over here. These ones are almost parallel to the edge, but these three, each of these there's your 90-degree angle, 90 degree. So radial fractures form right angles on the reverse side. Here's the reverse, this is the reverse side. This is the side that the projectile came from. So this is the front, we'll call the front, and this is the back. So this is the reverse. So the reverse side should have that right angle, right angle, right angle. Okay? So therefore, if you see the right angle on the reverse side, it's a radial fracture. But if you see the right angle on the front side, then it's not a radial fracture, but it's a concentric fracture. Okay, so the center one is a radial fracture. So I know that's radial, therefore if the right angles are on this side, the projectile came from the left. If they're on the left side here, then the projectile came from the right. And this way you can reconstruct the crime scene. You can tell Now determine which the bullets flew from which way. Was it from inside the building, outside the building, inside the car, outside the car, and reconstruct your crime scene. And also this last bullet here, the sequence of impacts when there have been successive, more than one penetration, is frequently possible to determine because the fracture always terminates at an existing line of fractures. So for example, all right, you got one bullet hole here, you got another bullet hole over here. All right, you just look at this thing. Which one do you think, just from looking at this, occurred first? Okay, well, they look basically the same, other than these radial fractures seem to go unhindered, whereas this one here is terminated, and this one here is terminated. That means that this one occurred first, and this bullet hole happened second, because when it cracked, it stopped and it didn't go through. That's how you can tell which one was first and which one second. So you're just adding evidence to the crime scene, adding your ability to reconstruct a story. Okay, so now let's go through and actually do a live demonstration of taking a piece of a window pane or a piece of glass and shooting a projectile through and looking at the stress marks and seeing if we can determine which direction the bullet came through. All right, let's do this. All right, guys, time to test your knowledge and see if you truly understand the 3R rule. All right, so I just took a piece of glass here. I'll fire a projectile. Okay, and it looks like the concentric fractures aren't so noticeable, but that's okay because all we really need are the radial ones. We're going to look at the radial ones under the dissecting scope, but let me just fire one more here through the glass. Okay, wow, and you can see the radial fracture going all the way across. Okay, so what I did is I just took a piece of glass with an edge formed by a radial fracture. You see that on the top there. I wrote the letter G, and I'm gonna tip the glass like this. Okay, so you can see the G then will be towards the bottom of your screen. Now, I want you to look into the dissecting scope, find the 90-degree stress marks, determine if they're on the top of the screen or on the bottom, the top edge or the bottom edge, while you're looking into the dissecting scope. And from there, answer the question, did the bullet strike the side with the G, or did the bullet strike the side without the G? Notice when I turn the glass downward, the G is, towards the bottom of your screen. All right, so let's take a look. What do you think? The 90-degree stress marks, there they are right there. I can see them. It looks like the stress marks form 90 degrees at the top side or the bottom side there. Letter G, once again, I'll turn it, down so the G is facing down the bottom of the screen, and those 90-degree angles are at the top. Okay, so they're towards the top of the screen. Therefore, what side did the bullet strike the glass? With the G or without the G? From the G side or without? The answer is from the side with the G. Why? Because the rule is, if it's a radial fracture, it will form right angles on the reverse side. And there was actually one more thing that we talked about earlier in the talk. Radial fractures tend to blow out on the reverse side, on the back side. So if you look at this piece of glass, you can actually see, okay, yeah, this side doesn't have the glass blown out. The other side does. Therefore, that must be the center, and the side right now would be on the right side of the screen, must be the reverse side. So that's another way to determine bullet direction, projectile direction. All right, guys. Well, thank you very much for watching. I really hope you enjoyed, and we'll see you next time.